Welcome back today. So we have two lectures today. The first one is by Lina Roald. So she's an associate professor at the University of Wisconsin-Madison, and she's done a lot of work on optimization for power system operation and resilience, especially under uncertainty and rare events. So she's going to talk today about topology optimization for system resilience. Remember, when you have questions, please use this mic for the recording. So I will leave it here in front and try to pass it around, although I'll stand up and bring it when you have questions. Lina.
Awesome. All right, yeah, okay. Oh, can you hear me well? I feel like I can hear myself as well now. So thank you, Lizia, and welcome to the last few people who came in here. There's probably more coming, I guess. And yeah, good to see you here again this morning. As Lizia said, I'm going to talk about topology optimization, and I will talk about the particular kind of topology optimization. As I said, it will be in the context also of system resilience and restoration. But I thought topology is something that kind of carries across many different problems. And since you are here to learn things that can be helpful, hopefully, for your PhD and research in general, I wanted to try to generalize this a little bit beyond the specific topics that we've been working on in this context. So I'll talk a little bit about modeling choices that we can make in terms of power flow, how we model wildfire risk in problems, and so on. One thing I'm going to preface this with is that I'm here in Copenhagen. Some of you might have seen Arjun when we had our event on Sunday. He did not sleep very much this night, and as a result, I did not sleep very much this night. So if I stop making sense, please interrupt me, and we can all take a break, okay? So if you need a break, let me know. If you think I need a break, let me know. Okay. So we're going to start with some fun context here. And the context, I guess we're here for, is that we need a strong grid in the world. And in particular, as we're moving into the energy transition, we really need a grid that is stronger. So here on this slide, we're starting slow here today. We have, this is just a news release from last fall, EIA, who was reporting on how important the grid is for the energy transition, and that a lack of ambition and attention to the grid could risk making the grid itself a weak link in the clean energy transition that is happening across the world. Oh, good. Okay, good. So that is really kind of a global thing. Now, in the US context in particular, we are going through some really interesting times for the grid. So I think most of us have lived through this period in the grid, at least for me. Since I started doing research in power system, demand has been pretty flat. There hasn't been a lot of load growth. And we're really entering a period now where we are hoping for a lot of electrification of things like heating, EVs, but then also there's another rapidly growing source of electricity demand, which is data centers. And so these are just some headlines from this spring in March. And you can see when the Washington Post and the New York Times are writing about how the grid is a bottleneck in the US, it is becoming kind of a mainstream problem. So people are starting to pay attention to the grid also in the US in a way that kind of, I would say, they haven't for a long time. And I'm not really sure it's a good thing, but okay. One good thing that has come out of this is that in just the last 2 weeks, we've had some really good rulings coming out of FERC, the Federal Energy Regulatory Commission in the US, which has started to require long-term planning from regional transmission operators and independent system operators. So essentially, every grid in the US now needs to, except for Texas, which is not regulated by FERC, they now need to do long-term planning. That sounds like a no-brainer, but they haven't been doing so. So now they have to, which is good. It's also, so this is the first stop here. The second thing that also came out in the last 2 weeks is that FERC will now be able to kind of force the building of power lines and be the ultimate decision maker on whether a power line can be built or not. This has also been missing in the US, which has made it very hard to build power lines. So this is a good for grid expansion. And then there's been, I mean, they also released an assessment. This was just on Friday, which essentially just says there's a lot of demand growth. There's a lot of issues facing the grid, and we need to do something. And so all of this is just to say we need a stronger grid. We also need a grid that is more resilient. We heard about this yesterday. I am going to talk here in particular today about wildfire risk. There's a lot of other threats that are facing the grid as well, but that was something we will come back to. And then we also need a grid that is affordable. And so as we are thinking about how to make the grid more resilient, there are many ways in which we can do so, and achieving that while also making sure that we don't increase electricity prices to make electricity unaffordable is really important. And so here in particular, since I brought wildfire risk as an example of need for resilience, I also wanted to point to the recent wildfire risk mitigation things that have been happening in California. So PG&E, the utility there, has wanted to underground a lot of lines in order to reduce wildfire risk. And the result of that is that electricity rates in California are set to increase by approximately 13%. And so as this comes on top of already increasing cost of living and so on, and the actual reason many people cannot access electricity is, I mean, the reason most people experience power outages in their homes is not that the grid is failing, but rather that they cannot pay their bills. And so affordability is really, really important. In the US, something in around 20% of households are experiencing energy insecurity, meaning that they are struggling to pay for electricity and energy that they need. Yeah, great. Cool. So I thought I will do a little bit of an introduction here so that we can also get more people here. Great. So where is the topology optimization, which I promised? What I will say is that topology optimization matters everywhere here because the grid is so important. Here, what is topology of the power grid? Well, the topology of a graph is essentially the way nodes are connected with each other. And so the topology of the power grid you can think of as the way all these different nodes and buses in the network are connected to all the other buses. So this is the topology of the RTS-96 test system. I took this beautiful figure from a paper written by our EDTU friends here. And so this is kind of what we will talk about here is a little bit about how this topology interacts with all of those problems. So yeah, so an outline. So we have 3 hours here. I thought like, wow, 3 hours, that's a lot of time. So what should I try and teach you here today? So the first thing I wanted to talk to you all about is topology optimization. What is it and why is it useful? And the goal here is really just to kind of that you all should understand what topology optimization is and how it can be useful in different settings. And then we're going to talk. I'm going to bring a simple example of modeling and optimizing system topology. And here, essentially, the idea is just to give you an example of how do we actually model this mathematically and sort of talk a little bit about the challenges that are involved in solving those problems. And so that's kind of going to be the introductory first part here. And then we are going to do some kind of case studies, which are going to look at wildfire risk mitigation and restoration, where we are going to use these ideas of like how we need to optimize the topology of the grid in order to achieve better, more resilient grid operations. Does that sound good? Yay, great. All right, so topology optimization, what is it? And why is it useful? And so here, again, since it's morning, I can see most of you have found your coffees, that's great. I want you to take just a moment to kind of think about what are all the different ways in which the power system topology changes. So I'm gonna give you a few seconds to think about this. You see I have kind of written up a few different things on the slide here, sort of to spike your thoughts. And then I'm gonna ask you to come up with some ideas here. So. Okay, so anyone has any thoughts they want to share? How does the topology change? Yep.
Is built, would that be counted as a new topology change, or?
Kind of. I'm more interested in topology. I would say, like, yeah. I mean, you can change maybe how sometimes you need to change the topology of this particular bus, but you don't. You're kind of keeping the nodes mostly the same. Maybe you have to build a new line. Okay, yeah. But it's just the topology is really mostly about the nodes and how they connect. But that's a great point. Thanks. Yeah.
But if you have a new feeder and you want to keep radiality, it would change the topology.
Yeah, so if you have it, so in distribution, if you want to, for example, so say in distribution you have a feeder, you want to switch a line, or a tie line, for example, then you have to, make sure that you keep radiality. That is absolutely true. Why would be reasons you want to switch the distribution grid? Yeah, you could have a failure, or you could have, or it could be that you just have low power quality, right? I mean, like there's some, or at least we like, today we switch the feeder because we have failures, and that's the quickest way of restoring power to people. I guess we envision that in the future we will have more automatic switches and different things that we can do so that we can more actively change the distribution grid topology, right? While also hopefully maintaining radiality. Any other suggestions? Yep.
Power flows by splitting the buses.
Yep. So bus splitting. Yeah, we are going to talk about that a lot more. So all of you hopefully visited Giacomo's poster yesterday. You know he's an expert on this, and he will tell us more about it later today. So here we have so bus splitting to control power flow, and I have a little figure that shows what that means, but it essentially means that sometimes in these buses, the nodes in the network here, so bus splitting could mean that you, for example, are able to open a switch here so that you essentially split this bus into two separate buses. And then you can have things that are geographically very close, but electrically far from each other. And that can be a way of controlling power flow. Any other reasons?
The contingency and the line trips.
Yeah. Mm-hmm. So let's put that in the middle here, contingencies. Great, yep.
Energy storage is for contingency, as a flexible load.
Yeah, that's interesting. Okay, so let's see the generators, and let me say, like, kind of here also, let's connect some battery. Okay, I would say those are resources that are more kind of connected to the node rather than. So I would say these are resources that are really important, like the generator, very important resources for example, controlling power flow, but they don't really change necessarily how the graph is looking. But yeah, otherwise a really great point. These are very important, of course, for control. Anyone else can think of something? Yeah?
Open points for controlling the power flow.
Soft open points. That's a really interesting one because it's, yeah. Okay, so soft open points. Does everyone know what a soft open point is? So it's essentially like a switch that it's a power electronic device that allows you to control the power that is flowing, for example, across a tie line in a distribution grid. So it's essentially, so in distribution grids, you tend to have switches that you are open, typically open, normally open or normally closed. And the soft open points can be at that location, and then you can control how much power is flowing across it. Does that? Yeah. Cool. In the long term, short term, long term? Yeah. Yes. So transmission, I'm just going to say expansion, because if we expand the grid, then we add new, but of course we also have to plan it. Yep.
Wildfires destroying lines. So.
Yeah. Any other thoughts? Yeah?
Relations?
Yeah. So we have to make sure that we decide when do we open the lines for maintenance. So we have to make decisions about when to de-energize them. So that means the line doesn't disappear, it's still there, but it has to be off, right? Okay, cool. Yeah, I think we hit on pretty much all the points I had in mind, so this is great, thank you. So essentially, kind of, again, how are these similar and different? I mean, in some cases, we are looking at systems where, for example, a radial distribution grid, we want to keep it radial. In some systems, we have more flexibility, less flexibility, more redundancy, and then we have this long-term and short-term thing. So we we have where we have transmission expansion, which opens new paths, and then we have the more short-term version where we are able to control the lines that are already there in the system, and then we have these kind of forced outages, forced changes to the topology that happens because there's a contingency or a wildfire or something. And then we have the deliberate decisions that we make in order to turn something off, right? Or switch it around. So we don't need a slide. So essentially, transmission switching, here we can think of it as sort of turning the lines in the system on or off. I put lines here in quotation marks, because it doesn't necessarily have to be a line. It could be a bus bar or something, or a switch. And they can represent switching actions, as we said, closing or opening of switches, to control power flow in the so switching actions to control power flow in the transmission grid can be closing or opening of switches in distribution grids. We can do preemptive de-energizations, for example, to reduce wildfire risk, which we will get back to later. We could think of this in the context of restoration, where we have to make decisions about which line to repair first after, for example, a major storm. We have to think about this during planned maintenance operations, and then when we build new lines. And so this is just to say, these are just examples. This is just to say that this idea that we have to switch lines or kind of change the topology of the system comes back in a lot of different problems. I do want to talk about, just for one moment, what this means in normal operations. So topology optimization or transmission switching in normal operations. We are not going to talk about that much here, but I just want to say it's a really, really important thing. As we said, we will hear more about this also later today from Giacomo. But there is the main reason this happens, or the main thing that happens here in transmission grids is substation reconfiguration, where you, for example, decide to split the bus bar, or so you can do bus splitting or bus merging. And essentially what happens here is that you kind of have these nodes that we are looking at in this network. Actually, in reality, it's much more complex than just like a node that connects everything. In reality, you have these bus bars, and then when lines come in, you have a choice in which bus bar you connect them to, and whether you connect the bus bars to each other. And so you have a series of, so essentially if you can think of this as one bus bar, another bus bar, and then you have 4 lines that come in here, so 1 line that come in, 2 lines, 3 lines, and 4 lines. And these little squares here in this node, they represent, breakers that can be open or close. And so, for example, if you have a fault on this line, you could now disconnect that line entirely, or you could choose to disconnect these bus bars from each other, connect 3 lines together, and 1 line separately, or different kind of configurations that you can consider here. And so that is what this means. Like when we're looking at this kind of branch and single line diagram of the network, we don't see all these breakers. But in reality, this is very important for controlling power flow in the grid. There's also an option of actually turning off transmission lines. In normal operations, it's not used very often, but you can use it to control power flow. In some cases, turning off a line will help you increase power transfer capacity. In other situations, turning off a line can just help reduce overloads in your system. So for example, I have visited transmission system operators who were unhappy about how their neighbors were using their phase-shifting transformers, causing overloads on their lines. And so they said, okay, we'll just open our line, and then they can deal with their overloads again. So there's like kind of things like that can happen. That doesn't sound like they are coordinating. They are coordinating, but there's a lot of things to coordinate. Okay, so when we are looking at this, there's a lot of practical considerations that go into this. And one thing that is really important to know, I think, is that this type of topology optimization that happens in the transmission grid is very, very widely used in order to ensure economic, efficient operation of the grid in Europe. So in Europe, this is the first course of action that the transmission system operator is going to take in order to try and relieve congestion. And the reason is that it's very inexpensive. You just open these switches, and then you can change the flow. In the US, this is not incorporated in the market clearing at all. Partially because it's hard to incorporate discrete variables in the market clearing, but also because it is not the ISO who runs the market who also controls these switches. These switches are controlled by the physical owners of the infrastructure, which are different from the market clearing, the ISO in the US. And so that really means that makes a huge difference in how this type of topology optimization is being used, for example, in Europe and the US. And the reason I'm telling you this is because I got to know, I grew up in Europe thinking that topology optimization is such a cool tool. Then you come to the US and no one talks about it. And you're thinking like, why is that? This is really odd. But yeah, it comes down to who is it that owns who is it that actually, can push that button to open the switch or not. And then, of course, in order to do this kind of switching, we can solve optimization problems. What we are going to do here, what I'm going to show you here today is all steady-state optimization using power flow, so about power flow control. But it's important to know that particularly when you're talking about these type of transmission switching operations, it's really not only about power flow. There's a lot of other considerations that have to go into making sure that the resulting topology is actually feasible. For example, such as short circuit computation, so just making sure that short circuit currents don't become too large. And this is just to say there's a lot of complexity here that we are not going to go into detail. Also today, I am not going to talk about bus bar splitting. We will hear from Giacomo about that later. But I will talk primarily about the idea of switching like lines being on or off. So, and when I say lines, I really actually means the lines, the things that are here and connecting kind of buses that are far apart. Okay, so that's just kind of an overview. And then I just also want to say, forever here today is going to say 9:41 on my iPad. I don't know why that is, but every time you connect the iPad to the computer, it says 9:41. So don't get fooled. We are not yet at 9:41. And we will pass 9:41 and we'll still say 9:41. So yeah. Okay. So with that introduction, I wanted to talk a little bit about, sort of give you an example of optimal transmission line switching. How many of you have kind of seen this or worked with it before? So a few. Okay, good. That means that hopefully many of you are going to take something away from this that is helpful. For those of you who have done this before, maybe this is a bit of a recap, but hopefully still helpful. Okay, so we're going to start from the DC optimal power flow problem, which I assume that most of you are familiar with. Maybe shake your head if you're not, or nod your head if you are. Yeah, okay. Good. So essentially, the DC optimal power flow problem is what we kind of think of it as here. This is a problem that minimizes cost, subject to some nodal power balance constraints, generation limits, transmission line limits, and DC power flow formulation here. And so essentially, if I want to now modify this problem in order to represent transmission switching, does anyone have any idea about like where is it how do I need to do this? Where should I start? Adding binary variables. For what?
You just adjust the capacity of the line.
So adding binary variables to adjust capacity of a line. Very good. So which constraint would that be?
The third one.
The third one? So here? So you're saying, let me add the binary variable over here. Okay. Only there or on both sides?
It should be both sides.
Yeah. Okay. Great. That's cool. Why do they need to be binary?
Because we are going to switch it. So
yeah, it's a discrete decision, right? I mean, we either have it on or we have it off, and that is, we can represent that using a binary variable. So this Cij variable is going to be either 0 or 1. If it is 0, it means the line is off. If it is 1, it means it is on. Okay, great. Thanks. So that is good. Is there anything else we need to add here? Yeah?
Yes, because you are changing also the voltage. Like you need to put the same binary in the DC in the last constraint.
In the last constraint here, yes. So I can, for example, set this here. Yeah. So then I would also make sure that I essentially put not only this to 0 up here, but what would happen if I don't add this, then I would force these angles to be the same, right? Very good. This is really important, people. Okay, so if I force just the power flow here to be 0, without also doing something to the DC power flow constraint, I'm going to force theta I to be equal to theta j in order for there to be no power flow on that line. And that is really bad. I mean, that's really not what we want. What we want is that when we are switching the line out, the angles on each side of it can be anything. Okay, great. So that's pretty much exactly what I had written here. So thank you. Great. Is there any problems with this?
Yeah. Exclude. Sorry.
Depending on the number of binary variables, you have your trees that is growing too much, and so you're adding complexity.
Yeah. So problems, complexity. That is definitely an issue. I don't think we can get around it because it is a discrete decision whether we have it on or off. But yeah, definitely we are adding a lot of complexity to this problem. So thanks for pointing that out. I heard from you here as well.
Should we just exclude some of the lines from this switching? Because we can't just like turn off some of the lines basically because there's no switches there or some other technical issues.
Oh yeah. Yeah. So complexity, so I will say maybe not all lines can be switched. And this is particularly very true if you are looking at distribution grids. Most lines will not have switches. In transmission, it is fairly common that all lines can be switched. Yeah. Any other problems with this formulation as it is here? Yep.
The last constraint is not linear anymore.
Thank you. Yes, nonlinear. This is nonlinear now. We have a bilinear problem here, product between the theta and the Zij, and that is a problem. Does anyone know how we can get around that? Yeah. Yes, great. So we can use the big M. So what we are going to do here is that we are going to add what we are going to replace this constraint here with the big M constraint. And essentially, instead of saying Pij, the power flow on line from I to j has to be equal to these thetas, like the power flow times Zij, we can also reformulate it in this way. And so essentially here, what you see is that I've taken the equality that we had before, and I've split it into two. So if C here is 1, meaning that the line is in operation, then this becomes 0. And so this whole term disappears. And then you can see that now we have Pij should be smaller than or equal to minus Bij times theta I minus theta j, and go greater than or equal to, we get back to our equality. However, if I set Z is equal to 0, meaning it is turned off, I am essentially saying Pij has to be smaller than this, plus some big value, M. And Pij has to be greater than this, minus some big value, M. And so by choosing these M values appropriately, we can essentially both force Pij to 0 through this constraint, and make sure that we are not forcing those theta angles to be equal. And at the same time avoiding any bilinear products, right? So these are the three things we want. We want to force Pij to 0. So this should be equal to 0. This should be free. And it should all be linear. Okay. So then how do we choose M? How do you choose these big values? Anyone knows? It needs to be big enough. So M needs to be big enough that these that we actually get that these values here are free. So how to choose M? So it needs to be big enough that it does not constrain the problem. And then we also... Is there anything else I need to think about here? Can I just choose it to be equal to infinity? I mean, I guess I kind of could, but I want it to be as small as possible for numerical reasons. And the reason for this, why do these big M constants matter numerically? So essentially the thing here is just that, I mean, as you probably are aware if you've done any optimization, is that we cannot solve discrete problems directly. It's impossible. And so if I'm looking at the problem which has continuous variables, I have solution algorithms that help me find the optimal solution to that. And the reason continuous problems are easier is because when they are continuous, if they are also differentiable, we can find sensitivities. So that is what the optimization algorithms typically rely on to find optimal solutions. However, when we have discrete variables, we don't have those sensitivities. And so that's why it becomes so hard to solve the binary problems. So despite now only having two options for my binary variable z here, it is much harder to solve that problem than if it was a continuous x. And so essentially, all integer programs are solved by solving a sequence of relaxed problems. So essentially, have written this the wrong way around here. So I need to replace z, the discrete variable, by x. So now I have essentially relaxed my problem by saying, instead of having a variable that can only be 0 or 1, I allow it to be anywhere between 0 and 1 as well. Does everyone know what the relaxation of an optimization problem is? Yeah? Okay, good. So essentially what the relaxation is that if I'm still going to do it, let's say this is the feasible space of my original problem. And then the relaxation is something that contains the whole feasible space, and possibly more. Okay, and so when I do this, there are different algorithms that can be used in order to try and solve these problems. So we can have branch and bound algorithms, cutting plane algorithms. And essentially, the thing here is that the better our relaxation is, so the better, when I do this replacing of the binary variables with continuous variables, the better, the more closely that relaxed problem resembles the feasible space of the original problem, the faster I typically can find a solution. So what does better here mean? Well, better means essentially that I'm finding a relaxation that is as close as possible to the convex hull of the problem. So essentially, you can imagine if I have many points here that are discrete, they represent solutions to my problem. I can have a set of constraints around them. And now the feasible, and say I have an objective function that goes in this direction, right? Now the feasible points here is this point is all the points that are inside of these constraints. And I kind of want to find a representation now. If I just solve my relaxed problem here, I typically maybe can find the solution that lies here. And that is not an integer solution. And so I want to find a relaxation that is as close as possible to kind of containing these points that are feasible as possible. And I'm going to just show you this very quickly, because I think it's an interesting takeaway here, and also for anyone who does not only topology optimization, but also works with big M constants, this can be hopefully a helpful insight. So imagine here I have a problem where I have a variable x that needs to lie between 0 and 5, and I have a variable z that is either 0 or 1. And essentially, if I choose an x that is greater than 0, then I have to set z is equal to 1. So now you can imagine this could be a power flow on a line, needs to be between 0 and 5. And if I'm going to have any power flow on that line, z has to be equal to 1. So this constraint now can be expressed as x is smaller than or equal to m times z. And now I can, where m is this big M constant. And so now again, I'm back to how do I choose m? So one valid choice is to say I'm going to set m is equal to 10, because that doesn't constrain my problem, right? I can, if z is 1, then x can take on any range. And at the same time, if x is going to be larger than 0, z has to be equal to 1. Is this a feasible choice? Yes. Is it a good choice? Maybe, maybe not. Essentially, let me try and explain why this is maybe not the best choice. So if I now do the linear programming relaxation of this, I know that x has to be smaller than 5, and then I know that x has to be smaller than 10 z. So I can essentially get this if I draw this, I get this feasible region here. And what you can see is that this is sort of kind of large region. If I now choose, and this is because my m is 10. So the slope of this linear constraint here is because I chose m is equal to 10. Now, if instead I choose m is equal to 5, is it going to be better? Yes, we will get a smaller feasible region for the LP relaxation of this problem. So now I'm going to be in this region over here. And essentially, what I have done here is that I've actually this tightest bound that I'm using here. which is drawing on M from this bound on X, is that what happens is that I actually get the convex hull of my original feasible space. So this is the smallest possible feasible space I can get when I relax the problem, while still also wanting to contain all of the points, right? Why does it make, I mean, so that kind of maybe makes sense? Does it make sense? Having a tighter relaxation is better? Can anyone tell me, like, why is it important? I mean, would I get a solution quicker if I do it like that? Yep.
Well, if you have a tighter solution so that it's actually equal to the convex hull, then the linear relaxation will give you the integer solution.
Correct. So essentially, in linear programming, the solution always lies at the vertex of or there is at least one vertex that is optimal. And so if you think here that the solution, I mean, if I'm solving an optimization problem over this, I should find either this solution should be optimal, this solution should be optimal, or this solution should be optimal. And as a result, any solution that I find is now going to be also an integer solution. In contrast, if I have this one here, then I would also have a solution over here, which could be possible, maybe optimal for the linear program, but would not be an integer for z. Right. So that is kind of that's the reasoning behind this. In general, is it easy to find a convex hull? It was very easy here. In general, it's not that easy. Here also we have a very clear upper bound on M. It's not always that we have such a clear upper bound. But if you're doing big M optimization with big M constants, it's really important to try and find the smallest constants here as you can. Okay, so back to this. How do we actually find this M here now? Because so it can be challenging to know exactly how to define this. One way of going about finding an big M constant for this switching problem is to essentially pull this into the inside the brackets here, and leverage the fact that we often have bounds on how large these the angle differences between nodes can become. You can derive those either from stability limits or from power flow limits. So if you have a line that is energized, it automatically gives you a bound on how far apart the angles can be based on how large the power flow can get. And so you can leverage those to get sort of loose bounds on how large the angle difference could become between two different nodes. And so if you insert those numbers here, then you have a valid big M constant. It's possible that you can also get tighter values here, depending on the type of problem that you're trying to solve. It can be worthwhile to try and spend some effort, computational effort, of your effort, to try and figure out like what is the tightest values that you can find, because your problems might just solve so much quicker later. Okay. Any questions on that? Is it useful to go over this? Maybe, hopefully, I don't know. Yeah. Okay. Yep.
Difference in the voltage, in the angles. I understand that is used in the assumption of the linearization of the transmission or distribution grid. Right. The assumptions that we make. Is it also technically necessary in a physical grid?
To have the angle, the difference angle. Yeah. So it's actually kind of interesting. In the DC power flow, they don't hold the same importance as they do in an AC power flow. In an AC power flow, these angles are inside the sine or the cosine, right? And so when you're looking at an AC power flow, there are stability limits that determine how large your angle difference should become. You should, for example, never exceed 90 degrees, because then you will get an unstable power system. You also typically don't want to ever go all the way to 90 degrees. You want to have a little bit of leeway there, and so typically kind of a range of maybe 30 degrees is kind of a common for in an AC power flow problem. Here, you can think of it as if I say Pij has to be is equal to minus Bij theta I minus theta j. This has to be smaller than Pij max. So in DC power flow, I think it is better to essentially, if I now call this delta theta ij, I can bound delta theta ij by Pij. Well, it has to be greater than or equal. Yeah, it also has to be. Yeah, you can. Sorry, now I'm messing up with the signs here, but the angle difference has to be smaller than Pij max over Bij. And so that tells you, that gives you a bound, for example. Does that answer the question? Yeah. Cool. Yep.
Two nodes.
Yeah.
Doesn't the delta max changes because the nodes are further away, so you don't have the same constraint on the.
Exactly, yeah. So we don't want to enforce this constraint when the nodes are disconnected. So essentially, the way you obtain this bound is that you can think about a system that looks, say like this, okay? And say I have a lot of lines here. I'm just going to connect it all the way, okay? And so now you can think of what is the largest angle difference that I can get between this node here and this node there if I choose to disconnect this line. Of course, when I choose to disconnect this line, I don't know which other lines I have disconnected. It could be that I disconnected many of them. And so say I also take out a whole lot, like a lot of other lines as well. And in the end, I end up, essentially I want to find the longest path that I can get between these lines. And I think I should have thought of a better example maybe ahead of time. But you can think of, I can try and sort of make my way through this graph, sort of trying to traverse as many lines as possible to get, and then imagine that I have turned off all the other lines in the system here. And so you can essentially think that you can look at the number of node pairs that you have and then take away one, and then essentially look at, for all of those, you have some delta theta ij max, and then you can sort of sum across the entire system like that. And in this way, even though you have now disconnected these two lines, you know that, I mean, if I entirely disconnect them, so I also take away this line, say, then they are in separate components of the networks. It doesn't really matter that much anymore. But I do want to make sure that if they are still in the same connected component, that they can achieve any difference in angle that I want. Did that make sense?
How you compute this big M, because it totally depends on topology, so it becomes a variable itself, and you lose linearity.
Yes. So how do you compute this big M when you don't know the topology ahead of time? So you assume that you essentially have one really long string of lines that connect the two nodes, the longest possible string of lines, and then for each line you take the maximum angle difference, and so you sum across them. So essentially, since you don't know what the topology will be, you assume the worst case topology. Does that, yeah, okay, cool. Yep.
Last line, why did you use mean one?
Yeah, that's a good question. I mean, they would be, here, for example, if I assume that Pij max and Pij min are, if it's symmetrical, then they kind of become the same. But you could have situations in which the power flow in different directions, maybe in general, they could maybe not have the same bounds, and that could give you different angle bounds and so on. But yeah, that's the reason. I mean, in general, you could think of them as being the same, or the one, like delta theta ij min being the negative of theta ij max. Is that, yeah. So I think sort of...
distance, is it? Or
No. It's the smallest value, that you can get for the angle differences.
You didn't use mean for both of them. That's a smaller m, which is valid. Either of them
Okay, so
is
this is negative. So see here, theta ij max is equal to minus theta ij min. So one of them is large negative and the other one is large positive. Do you see what I'm saying? Yeah. Yeah. Okay. Cool. I mean, I think I could also probably equivalently here. Yeah. I mean, sorry that this is not clear. Yeah. Okay. Yeah.
Same then if they're.
That is what I also just thought of, and I wonder if I have made a mistake. There might be a typo on the slide. Sorry, let me check that. And I'm very bad at thinking loudly in front of you all. But I'll come back to you. When we take the break, I'll come back to you. Right, and I'll make some corrections on the slides as well. Okay, anything else? I mean, this is really good. Thank you all for engaging with me in this discussion and finding my typos. So then I want to ask you all, how hard is this problem to solve? I mean, we heard about the complexity here. Now we have added a ton of binary variables. That makes it hard. Does anyone know the technical term for it? Yeah, this is an NP hard problem. I mean, even the linear, the DC power flow version of it. Yeah. So essentially, oh yeah, sorry. Yep. Mm-hmm.
Still, I know a little bit about this weekend linearization, but for me, still you miss two constraints because also this theta should be moved between zero. No, you don't have negative theta between zero and a maximum. I'm talking about the delta.
Yeah, so you can have, so this angle difference here can go negative.
Delta, so it should be like a range between zero and a maximum, and between zero and a minimum, but always in between zero. Otherwise,
I mean, I guess it depends. If I take one variable, theta I minus theta j, and theta I, it can be negative and it can be positive. Right? The difference between them.
I'm talking about the delta.
Yeah.
The delta that you have delta, theta max, and the A.
Yeah. If I take the absolute value of the delta, it will be between 0 and a maximum value.
Yeah, because when I saw a different way to see it, like you have a binary, but the binary you constrain in the lower bound between 0 and a minimum. And a minimum constraint, and the maximum you have the same. You have the maximum between 0 and a maximum constraint. So still you have to fit the constraint in order to be in between 0 and someone. But I feel here like you have the possibility to have negative values in between the delta maximum and delta minimum.
Okay, so let me. As I said, there might be a typo in these equations, and I'm gonna go back and look at them. I'm happy also to take this more offline if you have any questions. The idea here is that there's a big value. Hopefully you all kind of get the concept that there's a big value. It can sometimes be positive. It can also be negative because we are looking at differences between angles. So it's not necessarily always an absolute value. And essentially you need to find the value that allows the difference between the angles to take on essentially whichever value you want it to be. Yeah.
The sign of delta theta actually gives you the direction of the bound
Exactly,
state.
yeah.
So it can go in one direction or the other direction.
Yeah.
It means that delta theta changes the sign from positive to negative. So it could be both, right?
Yeah, I'm not talking about the delta theta, I'm talking about the
the maximum. Is that? Yeah.
Minimum, like at the constraint.
Right, but now you can think that delta. So let me get back to this. I think we agree. I think on the fundamental level we agree, and I'm sorry that there seemed to be some typo in these equations. I'll get back to you all about that. Hopefully that will clarify it. Okay. Yeah. Okay. So in terms of this, as we are thinking about it, how hard it is to solve, clearly it is hard to come up with these constants. You need to be very careful about your signs, plus and minus. So the bad news here is that these are really, integer programs in general are really hard to solve. They are NP-complete problems. And what that means is that in the worst case, we have to check all possible combinations, so all combinations of variable values to find the optimal one. And just to give you a sense of this, because I don't know how many of you typically do integer optimization, but suppose you have a problem with n binary variables, and you want to solve it by brute force. And suppose you have a really fast computer, so you can check 10 to the 9th combinations of those variables per second. So if I now vary n, the number of variables that I have here, that I will get different time needed to check all the combinations. So if I have 10 variables, it will take me 1 microsecond. So if you solve a small problem with these integer constraints, you might think like, oh, that was really easy. But as you go to 30 variables, you then go to 1 second. As you go to 50 variables, you can go to 13 days. As you go to 70 variables, you can come to 374 centuries. And if you go to 100 variables, you have something like 3,000 times the current age of the universe, okay? So this is just to say that if you have to do this by brute force, 100 variables is not a lot. Typically, the problems that we want to solve here have a lot more variables than that. And so you need maybe a really, really long time to solve these problems. So that's the bad news. Doesn't sound very good. The good news is that, oh yeah, we have good processors. So if you look at the speed ups that have happened, so this is up till around 2016, okay. Since 1919, processors had a speed up of about 15,000 times. Okay, so they got 15,000 times faster. So now you can check a lot more combinations a lot more quickly. The even better news here is that integer optimization solvers have become a lot better. And so if you look at Cplex and Gurobi, who have been like kind of the 2 best solvers for this, you can look at a speed up since 1990 of about 850,000 times. So in combination, if I take this together, between 1990 and 2016, solving integer optimization problem, a typical MILP, became 12.7 billion times faster. So that's a lot, right? But what does that really mean? So it means that a typical MILP problem that would have taken 400 years to solve in 1990 can be solved in 1 second today. So this is just, I just want to call this into attention because I think that we read a lot about integer optimization in older papers and so on, which kind of essentially dooms it as being impossible, impractical, we cannot do it, it's too hard. So I just want to let you all know that there's been an enormous speed up here, so there's hope, okay? What is really important to know here is that this is a typical MILP. These problems are still NP-complete, they are still extremely hard to solve. You can definitely easily find instances where it still takes forever. And when we say forever, it could literally mean forever, like the current age of the universe, right? So it's possible that it's really slow, and that's important to take into consideration and kind of be aware when you're trying to solve this. So if you want to solve these problems efficiently and at scale in practical settings, you typically have to do things like exploit the problem structure. You have to be really careful about, for example, how you choose your big M constants, and so on. Okay. So with that, we are no longer at 9:41, but at 10. And I think it's perfect time for a break. Yeah, well, let's get started. So first, I just wanted to say sorry about, I am very bad at, I don't know. I guess many of you are teaching yourself or being TAs or something like that. I have a tendency to not be very good at thinking up front here. There's a very simple answer to what was the typo on the slide here. I think I must have messed up my my pluses and minuses. Essentially here, the only difference is that there should be one constant here, and it should be. Now I am getting even more confused, because if this is a large positive constant and there's a negative sign here, then that doesn't look very good. So I wonder if there should also be a minus, and I wonder if this should be a plus. But if that is the case, then we have a typo in our paper, and that's not great. So, yeah, okay. But yeah, so essentially, you want this term here. You want this term here in combination with the minus b here to be large, so that you are relaxing this constraint. You want this to be large and positive in combination with the b, which is the minus sign here is the thing that trips everything up, I think. And the same thing here. You want this to be kind of large and negative, so that you make those free, right? Is it better now when there's only one constant? It's only delta max, and it will be positive. We can agree on that. Okay, yay, okay, good, everyone, we are all in agreement. So yeah, let's move on from there then. Okay, so then we are gonna change gears a little bit. And so from this, which I hope was helpful to sort of get the brain started and like maybe recap something, maybe learn something new, hopefully, we are going to go into our case studies part here. And I will talk about the research that we've been doing in wildfire risk mitigation. And so just to kind of keep a little bit of this interactive thing here going, I wanted to ask, what do you think is the main risk factor in wildfire grid interactions? Yep.
Yeah, like the security of the grid will...
So there can be smoke. So essentially that the breakdown voltage becomes lower. Yeah, so you can get, essentially you can get flashovers more easily. And this is in general, when there's more pollution, you can get flashovers more easily. But in particular, if it's really heavy smoke, this can be a real problem. Yep. Oh, flashovers is, or arcing. So you get, so you essentially can get that, power lines are typically insulated by air. And now if you have a high voltage difference, then you can get, essentially if there's smoke, you can get essentially power flowing through the air. So there's an arc. So actually, this is a really good question. So have any of you ever seen an electric lighter? So where it's like, it has a button and you hit it and then it makes like a little blue thing that is, and then you can use it to light a lamp. That is exactly the concept, okay? That is exactly the concept. You have a potential difference, you have power that is flowing, like the current that is flowing through the air gets really hot. And that's kind of a flashover. Okay. Anything else? Yeah? Vegetation and wind, yes. What can vegetation and wind cause?
Just touching the land.
Yeah.
Spreading the wildfire.
Yeah. So this is, and so that, then you can get that effect, right? So if the vegetation comes close to the line, you can get that lighter kind of effect where you get the flashover onto the vegetation. Vegetation can catch fire, and then you have a fire that is burning. And if it's also high wind, it will spread rapidly. Great. Yeah. Also up there, yeah?
Heat of the fire.
Heat, yeah. So heat or burning. Yeah. Cascading effects, yeah. And this is particularly important when you have, if you can have many flashovers, right? The smoke, for example, can be something that can cause, or if you then have many lines that are out, that can cause outages. There's been reports of this where you have these many flashovers, and then you kind of get a cascading event, and you can lose a lot of load, a lot of transients in the grid, a lot of problems. Yeah. Mm-hmm.
You reduce the safe distance between the lines and the person, no?
Yeah, you should then.
So if you want to extinguish the fire, you need person surrounded there. So.
Yeah, firefighter safety. Yeah. This is actually really important because there is there's been some very sad incidents of firefighters being impacted by power lines, and in particular where the power lines probably should have been turned off in order to protect them. Because typically in areas where there's active fires burning, people are working on extinguishing fires, you have to turn off the lines in order to protect firefighters. If you don't do it, it can have really bad consequences. Right. Okay, well, great, thanks. So this is to sort of set it up here. So yeah, I'm going to recap a little bit of what we've been saying because you all are so good at knowing a little bit about this. But essentially, when we're talking about electric grid wildfire interactions, it's kind of important, of course, that power lines are being impacted by fires. So you can have increased flashovers due to smoke. You might need to do power shutoffs for the firefighters' safety. You can, of course, also have direct damage to equipment. You can see here, this is an example of the smoke, and you can see, that if you have a fire burning directly underneath here, this power line is hopefully not on. Of course, if you have also really just direct damage where power lines are burnt up, then the towers collapse. That's also bad. And yeah, these are just some pictures of firefighters near power lines. So this is really important, and it's an important consideration that power lines can be impacted by the fires. What is also important is that power lines can cause fires. So power lines can ignite fires. So we were talking about that effect with the lighter. So you can have arcing due to faulty equipment. You can have sparks that come from downed lines. So here are some. This is a picture from a paper by a group in Texas that shows the sparks coming out of a power line after it reaches ground. Here is a picture. I find it very fascinating that some newspaper had a picture of this arcing event near their newspaper. I think it's a really nice picture that shows how the arc can start and kind of go through a tree and come to ground. And I think it's important to also be aware that there are many operational practices in power systems that kind of promote or can lead to a higher risk of ignitions that are very common, like they are everywhere. And so, for example, if you have a fault on a line, it is typical that we have what we call reclosers. So the first thing that happens if there's a fault on a line is that you open the line. And then the next thing that happens is that maybe a second after or so, the line will close again because the fault might have been temporary. So you can imagine if there's a fault, for example, due to a lightning strike, it is just there for a very short period of time. If you open the line and reclose it again, the fault will be gone. Similar also if you have a tree branch that touches a line, it can touch. If you open the line, it can maybe fall to the ground, and then when you close the line again, it's gone. And so by doing this reclosing, you can get rid of a lot of faults very quickly. And so if you ever experience a power outage that lasts like 1 second, that is exactly the recloser at work. And so typically we reclose maybe 2 or 3 times on transmission lines. So in order to try and get rid of power outages quickly. And then another kind of thing that is out there is expulsion fuses. So fuses in distribution grids can sometimes just kind of explode. So like if you have a fault in the distribution grid, in order to stop that fault, you kind of have a small fuse that that explodes essentially, and that releases then also material that is very hot into the environment, and that can cause fire ignitions. So these are kind of just to say, because when you look at the power line, you don't really think that it will ignite a fire. It normally doesn't, but actually it happens kind of frequently. And when I say frequently, I mean hundreds of times a year in places like California and Texas. There are many ignitions. In places where fire ignitions happen and there's a lot of vulnerability to wildfires, there are many ignitions that happen every year. Most of them maybe don't lead to very large fires. But here are some statistics for fires this is from San Diego County, and this is a paper from 2015, but it still holds true. I know we have someone from San Diego, fires and power lines. You probably know a lot about that, but yeah. So essentially, if you look at the statistics of fires that are there, you can see that essentially very few fires are ignited by power lines. So less than 5% of fires are ignited by power lines, but those fires account for more than 25% of the area burned. And there are reasons for this. So fires ignited by power lines tend to be larger than other fires. And this is in particular because of high wind being kind of a common cause for both power line ignitions and large fires. So if you have a high wind conditions, there's a higher probability that you will see a power line ignition because there's a higher probability that you will see a fault. And because if you have an ignition, it's also more likely that the fire will spread and become large and harder to contain more quickly. And I will just say that these fires are not only large, they are also sometimes really, really devastating. And so some of the worst fires in recent history have been ignited by power lines. So there's examples from Australia, some of the more deadly fires there in the Black Saturday fires of 2009. They were ignited, several of them by power lines. The Camp Fire in California, both of which were very deadly. This is a more recent example from Colorado, where there was also a power line that caused a fire that destroyed more than 1,000 homes. Washington State in 2020 had multiple power line ignited fires all at once. The Dixie Fire in California was not as deadly as the Camp Fire, but it is the largest fire to burn in recent US history. And just also the firefighting cost was something upwards of $600 million. At some point, I think every second firefighter in the United States were in California fighting this fire. So it's just an enormous cost, an enormous effort to try and contain them. And then, of course, last year we had the fire in Lahaina in Hawaii, which was also sort of started by a power line. That was the originating cause for it. And so it's, yeah.
Fires this bad because they're not as easily detectable, because we don't find out about them until later on.
I think it depends. So why are they so bad, and why? So I think it comes back to this question that it often happens during very high wind conditions. So when the fire picks up, it just burns very quickly. And so in Hawaii and also in the Camp Fire, definitely the cause was just that it spread very rapidly once it was. So it was very little time for people to evacuate, to get away before the fire was just there. Yeah. Okay, and then of course here I'm talking about the U.S., California, Texas, the Western U.S. generally, Australia, but also globally, wildfire risk is on the increase, and so this is really something that is important, I think, for us all to consider. Yeah, so our goal in this has been to try and help to build models that help utilities plan better. So there's been a lot of scrutiny in the US because of these large fires on utilities that have them, particularly in California. I think the California utilities are very good at modeling and managing this risk. But there's a lot of other places, for example, in Washington, many small rural cooperatives in different parts of the US that are struggling with knowing how to actually handle this risk. And so what we've been thinking is that it's important here to build models that use publicly accessible data, have transparent risk models, and can help utilities optimize their investment and operations in a kind of a coherent way. And so this is just some a citation from the Seattle Times on a utility in Puget Sound saying that we really don't have the data or information yet. So yeah, these are gaps that would be good to try and fill. Okay, so with that, how do we think about modeling and mitigating wildfire risk? So first, in terms of modeling, one way of thinking about wildfire risk is kind of roughly speaking, the wildfire risk is the product of both a probability that we will have an ignition and the size and intensity of the resulting fire. So if you have a very small fire or you have a fire that burns with low intensity, it's usually not that bad. There's actually, I mean, many landscapes are fire adapted, meaning that they are meant to burn. That is a little challenging these days because ecosystems are changing so rapidly due to climate change. That also has an impact on how they burn. But if you have a place which has, for example, a lot of biomass built up because you have a lot of trees that have died, or you have you've been doing fire suppression for a long time, you tend to get very intense fires, which are very bad. And so the kind of data on this second part is very unrelated to power systems, right? I would say that the utilities, it's not their fault that the climate is changing. they maybe played some part in it. But yeah, I mean, I think it's a little harsh to say it's your fault directly. So they happen kind of to operate in an area where the wildfire risk is a lot higher in many cases. And so the kind of data you can find on this is things like, we've been using this quite a lot, what is called the Wildland Fire Potential Index. This is using satellite data, weather forecasts, and fuel models from across the United States to measure the potential for large fires. And so essentially this data is telling you, if you have an ignition, what is the likelihood that it will grow into a fire that is going to be large and problematic for you to contain. And so, yeah, as I said, this is not really something that utilities tend to directly control. It's something kind of, I mean, you can do better fire management practices and so on, but the utility only has their right of way, so they should do the vegetation management there. But whoever owns the forest and the land outside also matters to how the fire would spread. So the thing that utilities can control is the probability of ignition, and so that is where the wildfire mitigation efforts are focused. So if you, as a utility, try to mitigate risk, you are taking some measures to try and reduce the probability of ignition. And so one way of doing this is to try to underground lines. And one of the nice things about undergrounding lines in the context of wildfire ignitions is that it essentially reduces the risk to zero. An underground line will not cause a fire because it can't get in touch with vegetation. The drawback is that it is very costly. And so if we look at, as I mentioned earlier,
responsible for the costs of the fires that were caused by their lines?
In California, yes. It depends on state law, how exactly. So, for example, Hawaii and California are slightly different. So I think the court battles around the Lahaina wildfire are still kind of ongoing, as far as I know. But in California, PG&E has been held liable for the damages caused by their fires. Their equipment has started, meaning so they went bankrupt because of fires and had to kind of go through restructuring to come out of bankruptcy. So it's a huge liability for the utilities to be in an area like this. Because they have to try and manage it better. We could maybe argue, is that fair that they are held liable? I think there's a lot of questions around regulation, how you regulate utilities. I think one of the things that I find interesting is that the utilities, I think also particularly the California utilities, have been very resistant to they want to regulate themselves. And as a result of that, there aren't very many rules about what they are allowed to do and not allowed to do. And I think now it's really backfiring, because you can't say that, okay, these were the rules that were set, we follow the rules, and we shouldn't be held liable, because they essentially went bankrupt, is the short story. Yep. So that's also why they're very interested, of course, in avoiding more fires. There's a financial incentive as well. Any other questions on this? Yeah. So the other big financial incentive, we should say, is that utilities earn a lot of a defined return on investment when they are making capital investments. So there's a lot of, you can ask, I mean, PG&E wants to bury a lot of they want to underground a lot of lines, because then they can also go and tell the California Utility Commission that, hey, we need to underground all these lines, and we want to earn a rate of return on that, and we are going to pass all these costs on to the customers. So it's very important in this context with regulatory oversight. And so essentially they had initially said they will bury 10,000 miles of lines, power lines. They still say they want to do that over time. But in their most recent rate case, which is essentially the proposal they have to make to the regulator, they settled on they will bury about 1,000 miles of lines, but that will then translate into a 13% increase in PG&E customer bills. And I don't know, Manoush, if are you in PG&E territory? Yeah. Yeah, also similar. Yeah, exactly.
I will refrain from commenting.
Well, so there's there's a lot of things you could say about the cost of this, also in terms of who is paying for it, who lives in wildfire-prone places. There's some lot of rich people who live in wildfire-prone places because it's nice to live between trees. Who should actually carry the cost of doing this mitigation? There's also many poor people who live in very rural places where there's a lot of need for wildfires, so for wildfire mitigation. So I'm just going to say there's a very big discussion around this. And I think it's kind of a preview for many kinds of climate change adaptation questions that we are going to face. But yeah, because it is limited how much undergrounding you can do, it raises important questions about where to invest. And then another type of wildfire risk mitigation is just cutting trees better. So you can do better vegetation management, cut the trees more often, making sure that they are far away from the power lines. This is already being done, of course, and if you also do some better maintenance of your equipment, you can prevent it from failing so easily. But of course, there's some risk that remains here, and there's also a very significant ongoing cost to doing vegetation management, and that someone has to pay for that eventually. This is an as a aside, this is an operational cost, so does not get passed on to consumers the same way undergrounding does. Then there is another thing that you can do, and that is changing the protection system settings. So as I was talking about the reclosers, they close again and again and again, and every time you close again, you started one more of those like kind of lightning strike, like fire. It's like a push on the button on that lighter. And so you can also, so one way to try and reduce wildfire risk is to avoid reclosing as many times. But that again then has the impact that if there is an outage, then people are going to be out of power for a lot longer. And so if you change these settings, you also see that the number of outage hours for customers quite significantly increase. And so that is also kind of a challenge. And then it's also not so clear, still some risk remains. When I say some risk, it's partially because I don't know what that number of risk is, and I don't think anyone really does. So these are important questions now around, can we gather the data to actually do better risk assessment here? And then lastly, I think the last one I want to mention here is on public safety power shutoffs. And that's the one I'm going to focus on, so I'm going to talk about that in a bit more detail. So I don't know how many people here has heard about the public safety power shutoff? Again, okay. Yeah, our US, California, and Wisconsin participants. So a public safety power shutoff is the situation in which the utility goes and says, I'm going to turn off this power line because it goes through an area where there's a lot of trees. And now, if that line comes in touch with one of the trees, there could be a fire. This is too high of a risk. I don't want, the utility doesn't want it. Presumably no one else wants it either. So that's why they have dubbed it public safety power shutoff, right? For the safety of the public, to avoid wildfire ignition. So the idea here is to de-energize or shut off power lines in high-risk areas. And of course, that reduces wildfire risk. But at the same time, if I shut off the power line, I also cannot send any power across it. And so that means that people are getting power outages. But I first read about this and started reading the plans for these public safety power shutoffs. This was back in summer of 2019. I thought wow, this is really crazy. There had been some regulatory action that allowed much larger public safety power shutoffs. And sure enough, in October 2019, there was the largest such power shutoff to date. And so what I will say here is that this is very effective in reducing wildfire risk, but also, of course, highly disruptive to customers. So in this public safety power shutoff event, you can see kind of the scope of it. So this is Northern California in PG&E territory. About 2.5 million people lost power. Okay, that's a lot of people, and it's and for several days. Okay, and there's estimated that it cost something like $2 billion in economic losses. On the other hand, it avoided approximately 114 wildfire ignitions in a very high-risk time. Again, it's approximated that 45,000 people would have been directly impacted by those fires, and there could have been around 300,000 acres burned. It's very hard to know the counterfactual because the power lines were shut off, and maybe there was damage to the power system because of high winds, But like, what do we really know about those fires? We don't really know. What we actually do know is that in one of those areas where there was a public safety power shutoff, the distribution grid was shut off, the transmission grid was still on. The transmission grid actually started a fire, so not so great. So there's still a background risk here, and you can now ask yourself, like, okay, poor people, they didn't have power, but the transmission line was there and still serving other people. So you can see how there's a lot of kind of questions around, like, what is the local fire risk that you're mitigating? What are these like long transmission lines that, for example, serve load centers such as San Francisco? You know, like, yeah. So there's a lot of trade-offs here. Essentially, what we had started asking as this was happening was we were looking at all the rules that were being applied to understand when are these power shutoffs being implemented, and we wanted to see, is there any opportunity for us to optimize those, to make them better or less disruptive? And I see a question.
What to turn off and what to turn on? You're dealing with the transmission system or the distribution system?
So it used to primarily, I mean, so both. There's a higher threshold for turning off transmission lines. You should also say, so like per mile of line, distribution grids are 3 times more likely to cause a fire. And that's partially because you can imagine the right-of-ways of transmission lines are bigger, so there's like less trees directly there. They are maybe more well maintained because there's just much fewer transmission lines. But then also, if you think about it, like distribution lines are, because they're kind of close to the ground, there's many towers. Every tower has a set of insulators, has a set of components to it, is one component that can fail. And so just by having more components in the distribution grid, you also kind of get a higher fire risk. And so this is kind of like the probability of fire is different, and therefore also the kind of the thresholds that are being applied. But after this event, I think there's the Kincaid fire that was started during this power shutoff. I think they sort of thought about like how to do it better. Now my iPad is locking me out, sorry. Okay. Okay, so that led us to thinking about what we call the optimal power shutoff problem. Let me just say here, the optimal power shutoff is no power shutoff. But like here, the idea is to try and make it as small as possible and as effective as possible. Okay. Yeah, so how do we think about this? So we started modeling this, and there's a lot you could discuss. There are many different ways in which you could go about this, and we're going to get back to that later. But essentially here, the idea is that we want to maximize this objective function, where the first part of the objective function is trying to maximize delivered load. So this d tot here is essentially the total demand at every node that we are able to serve. And so d here is the total demand. xd is a decision variable that says how large fraction of load are we able to serve at this node. And then what is the weight that we assign to this node. And this weight is there to express some kind of load priority. It could be that you have critical loads like hospitals or so on, or community needs that you really want to serve. And so that can be why you might want to weight the nodes differently. So this is the first part of the objective, and we want to maximize that. And then on the other hand, we have a negative sign here. And the second part of the objective is that we want to minimize wildfire risk. So it's a bi-objective optimization. And the minimization of wildfire risk here is expressed in the following way. So we have this R fire, which is the total wildfire risk, which is the sum of the wildfire risk of all the components in the system. And so these R values here, they are derived using these wildland fire potential index from the US Geological Survey. And we overlay essentially the power line locations on this risk map, and then we derive these risk values for each component. You can see here that in front of each component, there's also a decision variable. X here is a continuous variable. These are binary decisions. And so essentially what we are saying here is that we can have a choice in whether or not we leave a line, a generator, a load energized or not. And if we choose to turn them off, we are also getting rid of all the wildfire risk. So if we de-energize, there is no risk of a fire ignition from this component anymore. And so, yeah, so this is essentially the sum of the wildfire risk across all the components, and Z is 0 means there's a 0 probability of ignition, it is off, or Z is 1 means that there's a non-zero probability, and that kind of risk of that ignition is accounted for by this R. I should also say here there's no explicit mentioning of probabilities here, and that is because we are assuming that that's kind of folded into this these wildfire risk values. Also, in absence of detailed probability information, we kind of assume that all the lines sort of have the same probability, except for we do some differentiation by voltage levels. Yep.
X.
So X is the fraction of load that is being served. So X, I essentially I say that I can continuously shed load. That's a little bit of an assumption here. I mean, it's not so easy to do, but that's the assumption. Okay, so that's our objective function. Now, in order to actually make this into an optimization problem, we also have to model, well, I should also say there's one part in this objective function I didn't talk about yet, and that is alpha. So you can see here there's an alpha and an alpha. That is a trade-off parameter. It's a parameter I set ahead of time to determine whether I care more about maximizing load delivery or reducing wildfire risk. So if I set alpha close to 1, then I'm really saying I focus on reducing wildfire risk. If I set alpha close to 0, I focus on delivering load. And so this, by changing this parameter, I can essentially trade off out a Pareto front. We have often gotten the question of why do we choose to have two objectives? Why not somehow assign a dollar value to load loss and a dollar value to wildfire risk, and then bring them onto the same sort of axis so you can just directly minimize? That was a very deliberate choice here because it's really, really hard to assess exactly what is the impact of losing your power for a longer time. It's also very hard when you get into assessing wildfire risk. You get into questions of like, yeah, I mean, people might die. It's not very easy to sort of think about how do you put a dollar value on that. I think I know that there is work on that. We didn't want to go down that path. Yeah, did you?
The wildfire risk, are those like standardized, or do they fluctuate from one data set to the other?
So in this, the map that is here, which is maybe not super easy to see, but there's this data from the this data from the U.S. Geological Survey. So the Wildland Fire Potential Index. It is something you can get for every day. This is released daily for the full day, so it's not an hourly. There's commercial products that will tell you hourly risk. And I think also increasingly those are becoming more available. There's been a very large change in what is available. So it's rapidly developing. But we essentially take this risk data for a given day, then you overlay the wildfire infrastructure on top of, or the power infrastructure on top of it, and then you can think about, you can kind of integrate along the line, you can choose the maximum wildfire risk. There's different ways in which you can take the wildfire risk values and aggregate it to this R value. And in fact, it's really important how you choose to do that. That's also something we've looked at. But yeah, that's kind of where those R values come from. So you take the ambient wildfire risk and somehow aggregate it to the line. Yep.
The database, no?
Yeah, it's a
across like 90 kilometers is the mean average of the old line?
Yeah,
so the maximum?
Yeah, so that's a really good question. So you can either look at, so it depends. So if you look at the whole line, you can integrate across along the full line to see what is the wildfire risk along the full line, and then say, okay, a longer line might have just a higher wildfire risk, and so we are going to kind of take that into account. That would mean, that maybe if you have a really long line, it would tend to have a really high value because even if the wildfire risk is kind of low along the line, it's just a long line. The other way of doing it is to say that actually for this line, what I really care about is maybe not the small values everywhere. I care about some regions where it's really high. And so you could then take the maximum value across all the different points on the line. That is maybe a little bit extreme again. Like, I mean, then you don't really differentiate. Then you can do all combinations in between, right? So there's different ways. You can threshold the values. There are different ways. And I have a reference for that later. We did some study on that previously. But yeah, and it's a really good question because it really matters. It really changes the decisions that are being made by this model. Okay, any other questions? Okay, good. I'm very glad you're asking questions, by the way. I hope that makes it more understandable. Okay, so given this objective function, this alpha parameter that can help us trade off wildfire risk versus load delivery, we of course have to integrate that into a bigger problem. Now we get to the topology optimization part. Okay, so here we are putting these this objective function to express the amount of load. We have to have these variables that determine how much load is being served, and then these are the on-off decisions that impact the risk. We have to see how does that impact the power flow. And so here, this is now a DC power flow formulation that models how the power system would operate while we are shutting off lines. And so there is a power balance constraint where you can see in this power balance constraint, we have again the variable for the load. We have the power flow constraints here with the big M values, and I'm again now looking at them thinking, are they correct? Don't look at them too closely, okay? But they are there. And then there's the generation here, generation constraints, and then we have some component relationships here. And these component relationships essentially just say that if a bus is de-energized, if a node in the graph has been de-energized, every component that is connected to that node has to be de-energized as well. We can't have a generator hanging out there by itself. It has to also be de-energized then. Yeah, so this is the formulation with the transmission switching, and the transmission switching here is really switching on and off whole lines in order to reduce wildfire risk. That's the goal, right? So again, this is a mixed integer linear program. We have a whole bunch of integer variables. We have a whole bunch of continuous variables. And in general, as we know, this can be a challenging problem to solve. So we will get back to the challenging part. But first, I wanted to just show you some results here. So I'm going to show some results on a small test case. So this is the RTS GMLC test case. I don't know if any of you have encountered this system, RTS GMLC. It is the RTS 96 system, the IEEE reliability test system, originally from 96. That's why it's called 96. It does not have 96 buses. And it was updated by the NREL recently to include a lot more renewable energy generation, and it was also assigned geographical coordinates. So this test case is kind of like a standard test case. It is located in California. It goes into Nevada and Arizona as well. But you can see it crosses through some areas that have pretty high wildfire risk in this like October 2019 case. In this case, we were not using directly the USGS data. We were kind of looking at this sort of simpler risk map. But yeah, you can imagine any kind of wildfire risk map underlying here that helps you assign risks to components. So essentially the risk values are based on California October 2019 risk. The device risk is estimated based on location. So the transmission line risk is averaged in this case and scaled for the length of the line. So essentially this is kind of like integrating. And then we have adjusted the risk based on voltage levels, saying that if you have a line that is at a lower voltage level, it has a higher probability of ignition for a given kind of background risk value. Okay, so what does this look like? So the first insight I want to give here is just that having this risk trade-off parameter is kind of helpful. So if I change alpha, I can obtain different solutions, right? So first, if I just imagine I'm setting alpha, I'm setting alpha to 0, meaning that I'm able to serve all of the loads. I don't care about wildfire risk. In this case, I'm going to back to my original RTS GMLC system. In this case, the risk here is a kind of a unitless value, which is in thread with like how this is being published. So higher values means higher risk, lower values means lower risk. And the total risk here is 746. Okay, so whatever that number means. And then the load that we serve in the system is everything that is 8,500 megawatt, 8,550 to be precise. So now let me do one thing. And the first thing I'm going to do is I'm going to choose a medium risk case with a pretty small alpha. So already setting alpha to 0.01, where we're putting a little bit of weight on the wildfire risk, actually helps us reduce the total risk by a lot. So by just thinking about wildfire risk in this problem, we are able to take a lot of lines out of operation because there's a lot of redundancy in this system. So now we're operating the transmission grid here kind of like a radio system. And we have a bunch of lines that have been de-energized in high-risk regions, so we have reduced the wildfire risk by 57%. And we are able to achieve that by only shedding 10 megawatts of load. So a really minor reduction in load served, but a very significant reduction in risk. And then you can also now think about, we can have another case. If I increase alpha and I say, actually, I would like the wildfire risk to be even lower, then if I set alpha is equal to 0.15, then I can reduce wildfire risk by 92%. And in that case, I would shed 15% of the system load. And so you can see on these graphs up here, you can see everything that is in green is lines that are in operation. So this is the same system across here. I don't have the wildfire risk underneath those. But you can see all the lines here that are green. They represent lines that are still in operation. Everything that is grayed out are things that are de-energized. And then the red nodes represent nodes with load shed. And so you can kind of see that there's more nodes that are red here than here, and more gray lines here than here. And that is because we are now more focused on reducing the wildfire risk. Rodrigo.
Demands. So that would be like reducing risk for free, right?
Yeah.
Could this happen?
Yeah, so I would say you can, so in this medium risk case, it's very, very minimal here. You could probably already reduce, you could probably reduce it. I mean, even if you say the load served need to be, all the load has to be served, because there's a lot of redundancy in the system, you could probably already reduce the risk without actually shedding any load here. Yeah, so that's kind of nice in this system, yeah. There's still some implications of turning off a lot of transmission lines because you're losing that redundancy. Now, if you have another outage, then maybe it leaves you more vulnerable, but maybe that is worth it. Yeah, so these are, I think, important questions. Yep.
The results, but I see that a lot of the nodes that were shut off are also in high population areas, or what I assume are. So y'all look into the population that were the population that was related to that node and how many people were not served, because that 10 megawatts seems to represent about at least 100,000 people.
I love this question. Yeah, so the question is, should we not only think about this in terms of number of megawatts that are being shed, but in terms of number of people that are losing access to power, like how many customers are being shed? And I would say, absolutely, we should. I think in power systems, we're used to thinking about this in terms of load shed, like, okay, we want to maximize the amount of power, but of course, we also want to think about the number of people. I think, so when we look at this map, I absolutely agree. Like this is a densely populated area, and I don't know if in the RTS, but it's an artificial system. It's a synthetic grid, so I would be a little bit careful about doing direct sort of comparisons with real how many people live there. I will show a little bit later that we have a test case that actually represents the California grid, which Aditya also has worked on a lot. And so in that grid, it is when you run these simulations on that grid, which is ongoing work, you can say much more directly who are the people who would lose power, and then you can pull in other demographic information and so on, which is why we developed that test case to be able to run these kind of simulations. Yep.
So I wanted to follow up on the Rodrigo's question. So in this model, the dispatch is inefficient, right? Because there is no cost in the objective function. So how the dispatch is actually determined?
Yeah, that's a really good question. The assumption here is that in the situation, the utility will do anything they can to serve the load. That shedding load is more expensive than any generation, and so your goal is just to serve as much load as possible. That is essentially that's the assumption that is happening here. So that's why we are not looking at cost of dispatching, because value of lost load is really high. Yeah, so that's kind of but yeah, you could imagine that you would probably try and you could take the result that you have here, you could take the lines that are there, and you could try and run maybe a separate OPF later to see maybe it's possible to achieve a lower cost dispatch than what is here, because this solution really does not care about cost. That's correct. Mm-hmm.
This is how can you do why no units and why have units and you can plus and minus.
Oh yeah. So essentially, you can think. So there are two different ways in which you can think of it. So the way I think about this objective function is that risk is a unitless number. It represents risk, and then load is measured in megawatts. That's load. And alpha is essentially kind of a conversion factor that converts between the two. And so another way of expressing this is that you could also normalize, for example, the objective terms to sort of make them maybe more comparable in size. We've done that in later work. This is kind of the cleanest formulation, which is why I'm showing it. But it's really, this alpha is kind of, you can think of it as a kind of conversion factor that deals with units as well. But yeah, great question. Anything else? Yeah?
So following up their question, how can we say like 15% shedding the load is better than 90% reducing the risk? Like how can we compare these two?
Good question. I think that so how can we compare the reduction in wildfire risk with the load shed that we're seeing here? Is it good enough? Is it okay or not? I think that's a political question. It's a little above my pay grade to answer. But I would say, I think that is kind of, so this is, I think, where, where kind of the societal impacts of power system operation really hits us, and it's probably not something you want to leave up to an electrical engineer to decide on their own. So yeah, again, I think so. So yeah, but let me actually, I will come back to that later. Yeah. So one thing I just wanted, so in one moment, one slide in between, and then we'll come back to that. So essentially, one thing I just wanted to point out in those solutions is that you can see that there are many islands in this grid. So there's an essential assumption here that if you have generation available at a node, you're able to operate this as kind of a microgrid or an islanded operation. That is kind of a strong assumption in some cases, but probably not an easier one to deal with than many of the other challenges. And so just one of the reasons we are able to actually have this large risk reduction without shedding a lot of load is because the generation is so distributed throughout the system. Yep.
Doesn't that contradict what you said previously, stating that if you have a lower voltage distribution, you raise the probability of ignition? So wouldn't having a transmission be better to reduce the risk instead of having a distributed?
Yeah, that is kind of a good question, right? I mean, so okay, so since lower voltage grids are more likely to cause ignitions, and then distributed generation would maybe be connected at lower voltage level, maybe this is kind of contradicting. So the thing I think is important here is that if you don't have low voltage distribution, you are also not serving load. So in areas, so I think there's a way you can also think about this as kind of a here we're saying that the transmission, so here we are looking at transmission here primarily, right? This is down to 138 kV. So the nodes here that are being shed from the transmission grids, these are places where the transmission grid would say, we are not able to serve load in this location, and so therefore you have to shed load. You could also imagine that in those locations, there's also a distribution grid, and maybe inside that distribution grid, they are already saying, actually, we don't want to, we're going to do a power shutoff here as well because it's too high risk to operate the distribution grid. So there's some important interactions between transmission and distribution here that you're very good, very well kind of in pointing out. Yeah. Okay. Good. All right. So we'll come back to this question of how do we actually trade off load and generation, right? Oh, did you have a? Oh, thank you. Sorry, it's somehow my I have to keep my laptop alive and my iPad alive here. So sorry, this is not the most. It's a little annoying. So thank you for pointing it out. Okay, so then we wanted to see, as I said, when we started out with this, we were interested in how does a method like this compare with sort of more straight off rules. And so you can imagine, I think, kind of current practice, the way this is being implemented is that there's a transmission risk threshold. So the utility looks at all of the lines, says this line is really risky, and this is a high-risk day, so I'm going to shut off that line. So it's a consideration based on the risk of the line, not on the power flow on that line. And so we wanted to see how does solutions that are obtained in this way compare with solutions that are obtained by kind of more holistically accounting for both load shed and transmission and wildfire risk reduction. And so we are comparing this kind of, I call it current practice, where you set a wildfire risk threshold, RL max. This is essentially, if you're above that threshold, you have to turn the line off. And then we compare that with a situation where we have this trade-off parameter alpha that we can vary in order to get different solutions. So we can vary RL max, and we can vary alpha, and then we can sort of see how does our wildfire risk and load shed change. And so essentially, I'm going to compare these solutions on this graph, where on the x-axis you have essentially, as we are moving from left to right, we are seeing higher load delivery. So we want to be kind of high here. And then on the y-axis, you're seeing, as we're going upwards, higher wildfire risk. So where we want to be is kind of like over here in the corner. Over here in the corner, as close as possible. And so what we do is that now we're just varying R max and alpha, and we obtain different solutions. And the solutions we obtain look like this. So you can say, as we are tracing out these R max threshold values, we get the orange solution. As we're doing the varying of alpha, we're tracing out the blue solutions. And what you can see is that our blue solutions here are kind of consistently lower than the orange ones, right? So meaning that for a given value of wildfire risk, if I'm willing to set a threshold for total wildfire risk in the system, say 200, then I am able to serve more load if I optimize my shutoff based on this optimization problem, as compared with if I use a risk threshold. Conversely, if I say I want to serve at least 8,000 megawatts of load, then I can achieve a lower total wildfire risk in this with our problem here. So we're kind of getting closer to that corner where we want to be. And so that is sort of good, right? I mean, yay, our optimization problem works, this tells us. But it's kind of interesting to also look at the solutions and see how is this possible. And so what we're going to do now is that we're going to compare these two solutions here, the star ones, to see how does the risk at individual lines look like. And so again, we're going to look at the graph here, where we are looking at one side, we are going to look at higher risk on the x-axis. So this is now the wildfire risk for an individual line. And then we are going to look at the power transfer. So how much power is being sent across it. And the idea here is that as we increase the wildfire risk, we would like to shut down a line more. But then at the same time, if I have a high power transfer, it kind of indicates that this line is important to serve load to customers. And so I'm going to plot all the lines on here. But first, before I'm going to plot the actual lines, I'm going to say just what would this look like in our threshold. So in our threshold-based method, we would just essentially choose a threshold here, and we would keep all the lines in operation below that threshold. So essentially, all the shutoffs are just based on how high is the wildfire risk. And this is an example of a solution obtained, as this is the solution obtained with that. And you can see that there are loads that are being shed and many lines that are being turned off. And in this case, the shutoffs are prioritized only based on risk. Then I can now look at the optimized shutoff, and so I can compare this graph with this graph, and you can see it's kind of similar. But what and also here, there's a lot of high-risk lines that are being turned off. But the main difference here is really that if I have a very high risk on some lines, I still choose to keep them in operation. And so you can kind of see here that there's a region in which if the power transfer is above a certain value, the optimization problem kind of considers the line important enough that it is being kept in operation, although it is very high, it's kind of comparatively high risk. Of course, there's also many high-risk lines that are being shut down. Another thing to notice here is that many lines that can be shut down off because they are not important for power transfer also end up getting shut off. So that's kind of also where we save on wildfire risk in this problem. So this is kind of the result of prioritizing power shutoffs, not only based on risk, but also based on the amount of load shed we see. And one question I wanted to pose then is like, which do you actually think is better? Like, who benefits if I do this kind of prioritization based on risk and power transfer? Who are like, we heard yesterday about market designs and how there will be winners and losers. Here we are talking about like kind of rules around how are we going to do public safety power shutoffs. Can anyone think of like who is it that would be happy about implementing this, and maybe who would not be so happy?
Yeah. I think the customers would be not happy because they're getting their power shut off, but probably the utility company is going to be happier because they're delivering just a little bit less power, so they're not paying that much, but at the same time they're avoiding a catastrophe. So.
Yeah, with the power shut off overall, they would be happier. I mean, they choose to do so to reduce their liability, right? Yeah, that is really an important point. So I would say that if I should choose now between this type of shutoff and this type of shutoff, I would say I think this is very easy. Like, I mean, if I'm in a utility, I look at the shutoff, I look at the risk value, I shut it off. If I'm a regulator, I can say, this is the threshold, you shut off your line. So this is kind of easy to implement. This one is harder because somehow the utility would have to document that we are keeping this line in operation because it's a line that is important for it to serve power. You could then like start other considerations of like maybe this line would sag more because it has a higher power transfer. Maybe that increases wildfires. There's many things that you can consider. But then you can also say, okay, so this is a little bit like that situation where the people near this power line, it's a high-risk power line. Maybe their distribution system has been shut off. But now this power line is is still energized in order to serve some people who don't live there. So if I live very near this power line, maybe I would also want that one shut off because it's a wildfire risk that is really tangible to me, my property, like where I live. And so I think these are kind of important considerations. I mean, so we look at, you look at this and you say, oh, okay, great. We can serve more load with less less wildfire risk. But actually, when it comes down to it, it also really matters who are the people who are experiencing that risk.
In these low risk nodes that are not served, right? In this solution.
Yeah, it's possible. We don't know. So there are many power lines that are being shut off that are low risk. So the question is, are there people who are losing power because of that when we are shutting down all these lines, right? And actually, so here I'm only plotting the energization status of the lines. I'm not plotting how high risk is a certain location with load. That would be a really good plot to make. Maybe I should make that next time. But I think what we are, in fact, actually we are working on that. But essentially, many of these lines that are low risk that are getting shut off, they are being shut off because it doesn't really hurt power transfer. So these lines are, of course, they have zero power transfer because they are shut off. But they are also lines that would, even if you turn them on, they are not necessary. There's a lot of redundancy in the system, so they have been shut off in order to essentially avoid any risk from them, but without causing additional load shed. Because that's the only thing we care about here. We don't care about cost, right? We care about load shed. Yeah.
Possible to use this result, for example, the high-risk high power transfer areas to then prioritize undergrounding of the
Yeah, so definitely. Can you use this problem to prioritize risk for lines for undergrounding? Yes, you can. There's been work in the literature that has done this. I mean, I think Alyssa Cody and Dan Moulton, they have some papers on that. I mean, we've done some kind of work in that direction as well. And this is something we also are working on when I'm talking about this California system, to kind of just look at like what would this look like in that system. And essentially, if you want to prioritize which lines should I underground, it's really interesting. This is when it gets really interesting, because this is a problem where your operational problem is an integer problem, and your investment decisions is made and should be made considering a whole lot of different days, right? I mean, many different days, many different wildfire risk scenarios. And so if you are doing that, you have this very interesting optimization problem where you're optimizing investments decisions that are binary decisions, like which line are we going to underground? And then your undergrounding decisions impact which lines have to be turned off here. So it's a sub-problem that has binary decisions, and yeah, as we already heard yesterday, also from Rodrigo, and these are very, very challenging problems to solve. So yeah, it is. So yeah, but you could definitely use this as a problem, as an input to try and decide which lines should you underground to avoid power shutoffs. Yeah.
Has two terms, right?
Yeah.
So they are in conflict, right?
Yeah.
So why they are just writing the problem in a way that it seems they have a linear relationship? Why we are not solving the problem in a with epsilon constraint model or something like that?
A very good question. So why are we not using an epsilon constraint? So like we can. Yeah, so it's essentially the way by varying this alpha, I am able to trace out this Pareto curve. So the curve of all the sort of curve that is traced out by the solutions here, you can consider as the Pareto front of this problem. You could also achieve the same thing if I now, for example, say I want to maximize load, and I use instead a constraint to say I want to limit the amount of risk that I'm willing to see in my system. I could also similarly trace out a Pareto front, and I would maybe get different solutions, but I could still find, by looking at different thresholds, I could find different solutions.
Those objectives are different, so if you are just assigning a value.
Yeah. Yeah, exactly. So that's true. I mean, I would say they are kind of equivalent. It actually can be very different in terms of solution time and so on. It matters in many ways how you form that objective. So it's a really good question to ask. But sort of like fundamentally, they would be the same thing. If I take the objective function here, and instead of having both terms of the objective, I now say I'm gonna I'm gonna maximize the tot subject to the R fire being smaller than some threshold t, right? If I then vary t, it would be kind of similar to vary alpha.
Be more happier with this, and maybe if we just change the approach with an epsilon constraint, so it would be more clear.
Yeah, I like that. I think that's a really good point. That you could, so if I have this kind of formulation instead, then maybe it is easier for me to assess who is kind of taking on the higher risk. I could maybe also be more clear about where is that risk. Yeah, this is exactly. That's sort of, this is, I think, exactly one of the cases where it matters a lot how you choose to model this objective. And yeah, I mean, in fact, this is, when I was talking about, like, I mean, this is one of the things that we are also thinking about, like what if you have a constraint like this, can you not only constrain the total risk, but you can also constrain risk more locally, and then in that way, sort of look more at the geographical spread of risk. Is definitely a very interesting question. So you can look at equity, fairness, a lot of different considerations like that. And also, I guess, winners and losers and more generally. Great. All right. So yeah. Okay, so that was this was a lot about modeling, and I will continue because I know that there's going to be lunch, but if we take a break now, I don't think we will come back here. So I'll take a little bit more time, and then maybe we can end a little early or something, okay? So yeah, so I wanted to talk to you a little bit about scalability and solution quality here. And in particular, so this is a paper with Noah Rhodes and Eric Haag, who's a very talented undergrad student who's working with us, that will be presented at PSSC next week. So if you're interested, come there. Talk to Noah, and if you happen to be at PSSC, come to Noah's talk. It's going to be on Tuesday morning, so the first session on the first day. Okay. So the question that is here that we kind of wanted to answer is that in our previous optimization problem, we were modeling it using a DC power flow approach, and then we were asking, are those solutions actually any good? And so here, I want you to put yourself into our head and try to help me answer, what does it mean that a solution is good in this context? Right, exactly. Because I'm talking about power flow here. The real question that we had was whether is the solution going to be AC feasible? Can we take the solution that we're getting with our DC approximation and actually implement it in the grid without breaking things? And so yeah, so that's what we did. We essentially, so you can think about here as sort of a sequence of things that you can do, where you solve the, so if I solve a mixed integer DC optimal power shutoff problem, there's one thing I can tell you, and that is that the solution that I'm getting here is not going to be AC feasible. That would be a rare event, okay? It never happens. So the question becomes, what is it we can learn from this solution that is helpful? And the solution, the interesting thing here is the on-off status of the components. So the reason we want to use a DC power flow approximation here is so that we can solve a linear mixed integer program. Because linear mixed integer programs are hard to solve, but nonlinear, non-convex mixed integer programs are way worse, okay? So we solve this mixed integer DC optimal power for shutoff problem. We record the on-off status of components. So we say like, this was de-energized and this was not de-energized. And then we take that and we put it into a continuous AC optimal power flow problem where we're trying to maximize how much power can be served. And in this case, we could also, for example, integrate economics, right, in that part. So this was how we went about solving that. And we were not only interested in understanding what happens when we solve it with a DC optimal power flow problem, we also wanted to kind of test other power flow formulations. And so essentially here in this optimal power shutoff problem, this blue part here is essentially the DC power flow approximation. And what we're going to do here now is that we're going to switch this out with other power flow formulations. And so here I had planned to do a little quick aside and say, who is familiar with convex power flow relaxations? Or convex relaxations of power flow? Okay, so, and does anyone know what is the difference between a relaxation and an approximation? Okay, I'm gonna do a very quick aside here because we still have half an hour after all. So sorry, 1 minute of your lunch. So when we are talking about think about this like solution space of this optimization problem as being something really bad and non-convex. So this is a non-convex feasible space. In fact, it's even worse than this. It is not even continuous, right? I mean, it's dots inside here. So this is not a really easy problem to try and solve. And so the way we typically do it is that we maybe add an approximation to it, or we do a relaxation. And so an approximation is saying like, okay, this problem is really hard. Let me try and do something that is going to kind of fit it fairly well, maybe particularly in some region I'm interested in. So I'm going to create this blue region here. And let's say this is a convex approximation. I mean, even more better is to do a linear approximation, but I didn't draw a polytope. If I had done a linear one, then this should have been like kind of straight lines around the edges. And then I can also do what is so the thing about to be aware here of the approximation is that it covers kind of part of the black feasible region here. So the feasible region of my original problem, these are all the solutions that would be okay to use. So that is this gray region. So you can see that my approximation overlaps with the gray region. But it has some parts that are outside. So the blue approximation here, some of it overlaps with the gray, and some of it is outside of the gray, and some parts of the gray is not part of that. So that is an approximation. Now a convex relaxation would be something that sort of tries to encapsulate the whole gray region inside a convex shape. So this would be a convex relaxation. The part about a relaxation, the important piece here is that it needs to contain the whole gray space. If we want it to be convex, it also has to be convex. Okay, so this is just to say, like, what is it and then there's been a lot of work in coming up with good convex relaxations of AC power flow equations because we like convex optimization problems, because they help us find global optimal solutions. They help us prove in feasibility. They help us find lower bounds. Lots of good things about them. So that was a little bit of an aside. Now, so what we are going to do here is that we're going to switch this DC power flow approximation out with some other power flow approximation. So the first one is just going to be the AC power flow. So this is the full nonlinear, non-convex AC power flow equations. I'm not going to go through what all of those equations are, but essentially it's kind of like nodal power balance for active and reactive power. We have active power flows, reactive power flows. We have power transmission limits, power generation limits, and voltage limits. So this is just to say it becomes a lot more complex when you have to consider voltage magnitudes and active and reactive power, everything. It becomes kind of even more complicated when you're going to look at the convex relaxation. So here, this is the SOC power flow relaxation, where we are essentially relaxing the voltage products in the formulation. So we are taking the voltages out of the equations, and we are replacing them everywhere with products between the voltages. And so again, I'm not going to really go through this. I'm happy to talk more to any of you if you are interested. But essentially, you end up with a whole lot of different equations. And this is a bit complicated. And then we are doing one that is simpler than the DC approximation, and that is network flow. In network flow, there is no physical limitations on where power can flow, except for we want to adhere to the power flow limits. So in this case, there's no voltage angles, nothing. You can just, essentially, if you have power at the node, you can choose which line to send it on, as long as you adhere to the power flow limits. So we were trying to look at these 3 different formulations in addition to the DC OPF and look at how good are the solutions that we're getting. And so then I wanted to say, does this look complicated? Particularly the SOC power flow, I think, is kind of involved to implement. The good news for all of you is that you are going to hear from Carlton Coffrin later this week, who is the lead person behind powermodels.jl. I know he's coming here to talk about quantum computing, but you should also learn about power models because it's a really, really cool tool. And so by leveraging power models in this work, we've been able to kind of do this switching in and out comparatively easily. So I recommend that. Okay, so what is it we see? So I asked the question, which of these power flow formulation actually gives us good solutions? And the way we do this is that, as I said, we solve an optimal power shutoff problem to determine the on-off status of components, and then we solve a continuous AC optimal power flow afterwards to check if the solutions can be made AC feasible by maybe redispatching generation. And so when we are doing this, here we're looking at the IEEE 14 bus case here. We're looking at 500 randomly generated instances where we are just randomly generating risk values and randomly chosen an alpha value between 0 and 1. And then we solve all of these instances of the optimization problem with our 4 different power flow formulations. And what you can see here is that the objective function here is such that it kind of aligns very well. So then DC and the network flow formulation maybe have slightly higher objectives than the SOC and AC formulation. When we look at the split of the objective between how much load are we serving and how much branch risk we are seeing, we see that they, again, align kind of okay, except that maybe the DC and the network flow, they allow for they have slightly lower wildfire risk in their objective. So in a way, those solutions are maybe a little bit better when we look at it like this. So this is when we're just looking at what comes out of the optimization problem. So what happens now if we go through the process of taking the integer decisions that were made in here and then put it through an AC optimal power flow? So what we see then is that the objective functions changes drastically for the network flow and the DC formulation. So essentially, the amount of load, so the DC power flow and the network flow formulations, they are very similar. They thought that they were going to be able to serve pretty much all the load. But actually, with the solutions they came up with, they had a lot of load shed. And that is not good. And And you can see that that means that also if I adjust the objective function that is here based on the load shed that I get once I run the AC optimal power flow, you can see that the DC and the network flow have really a lot worse solutions than the than what we thought. And so what this told us is that essentially using a DC power flow approximation in this problem is not a very good idea. And this is sort of significant because I think pretty much all the literature that I am aware of in this topic has been using that. So just as a warning sign. I also am going to say here that I'm only showing a result for the 14 bus case here, but this really holds true across a range of test cases. We've tested it on many different PGLib cases. Specifically, we were looking at test cases between 3 bus and 118 bus, and across the board, where we were able to solve the SOC and AC solutions, we found that they are just much better than the DC and network flow. For the cases where we were not able to solve the problem with an AC or an SOC solution, we could still look at how much the objective changes with the network flow and DC, and we still found that they are not very good solutions, unfortunately. So now we know that DC and network flow have kind of low solution quality, which is not great news because for SOC and AC power flow formulation, we have really long solution times. And so this is on a log scale. We are plotting the solution times for the different systems. You can see that network flow and DC are always kind of at least an order of magnitude below the the SOC. The AC is like a couple of orders of magnitude above that again for different systems. These blobs represent distributions of solution times across the 500 instances. That's why it's blobs and not dots. But essentially, I think the separation here is very clear. So you can see that network flow and DC, they are very similar. They provide similar solutions. They have similar solution times. They are similarly bad. SOC is much better than AC, as you can tell here. It's much faster. AC only solves up to a 14-bus system. The SOC solves up to the 39-bus system. But beyond that, we are not able to solve either AC or SOC in this case. I'm not saying not able to solve. It means it didn't solve in 30 minutes. Because we were solving 500 problems, we didn't have time to wait more than 30 minutes for them to solve. So essentially, the bottom line here is that DC and network flow, they are providing bad solutions, but they are kind of scalable. SOC provides really good solutions. It scales better than AC, but it's still really limited. And so this is kind of our ongoing work right now, is to kind of looking at how can we scale SOC better? Can we make it go faster and quicker so that we can use it for even larger problems? So this is a little bit about like how I think it's important to think about what does it mean that a solution is good? Because I think it's very important to not think that a good solution here needs to make both good integer decision and good decisions for the continuous variables. It is perfectly fine if this DC optimum power flow problem had a rubbish generation dispatch, as long as I can take the solution and obtain a good generation dispatch using a continuous AC optimal power flow. The important thing here is the on-off status. And I think this is very important in general when we're doing topology optimization and optimization problems with integer variables, is that many cases we have to solve an approximation to obtain integer decisions, but then we can do other things later in order to try and get a better solution. Does that make sense? Important takeaway, okay? If you ever have to solve an integer problem, remember that it's not always going to be possible to solve a really detailed model with that, and that's okay, as long as your integer decisions are good. Okay, yeah?
You set of slides, you were doing the comparison of what is done at the moment at the TSO and your model.
Yeah.
Now you're taking the solution of the optimization model and then doing the continuous AC optimal power flow. Have you tested the solutions from the DSO method with the continuous AC optimal power flow?
That is a really good question. We have not yet. We have, yeah. I mean, I think so. We have not compared those solutions directly. Okay. So let me just restate your question to make sure I understand correctly. So here, right? We were saying that we are getting better solutions than this one. Does this still hold true when we are putting it through the AC AC feasibility check. We haven't done that. It could be a really interesting one to see because it's not clear how they would compare to each other. I would kind of hope that our method would be better, but then again, who knows? I mean, I don't know. I can't really say, but that's a really good question. I will go back and check that, I guess. Yep.
But you can use them as a starting point, right? Just to try to give a warm start, maybe that also makes sense.
To try and give a warm start, yeah. Yeah, I think that's also an interesting question. I think, so yeah, there is ways, and we have also looked into that, like kind of trying to sort of help the problem a little bit here. There are things that you can do in order to try and reduce the number of low-risk lines that you want to switch. So for example, you say, I'm never going to, you could use this, like this Rmax threshold also to say, like, you could put an Rmin threshold and say that actually I'm never going to switch off the lines. I'm just not going to consider switching off lines for wildfire risk mitigation in order to, I mean, I don't want to deal with those small risk lines. They can be on always. That helps. You still have to actually, in this problem, be able to switch them off because otherwise you can run into infeasibility. Like, yeah. So there's a lot of, particularly when you go, and I will just say this, particularly if you wanted to solve this full problem with AC power flow, it's actually really challenging to make sure that you are able to always get a solution to this problem. It's like, there are so many quirky things that can happen here about like voltages that need to be able to go to zero and like other kind of things. And I see Giacomo is nodding. I think he's probably encountered that himself. It's just really challenging. To make sure that this problem you find a feasible solution is really hard in and of itself. And I think Carlton, I mean, I don't think he will talk about that here when he's here, but he did some really interesting work in that direction to try and ensure that you can always find an AC feasible solution, even in situations where you have a lot of damage to a grid or so on. So yeah. Okay. Any other questions here? Yeah?
Are we not considering line only? It's like a virtual grid kind of concept.
Yeah, so this is it. So let me try and draw it. So if I have a DC power flow, I am saying that the power flow across this line is a function of my voltage angles. So I have Pij. And then vice versa, I will have for all the other lines as well. So the in the DC power flow, this is how it works. In network flow, Pijl can be anything. You can choose the power flow across the lines as long as you just say Pijl max. It has to be within the bounds. But you're just allowing, essentially, you're allowed to break the Kirchhoff laws. You don't consider any physics. You're just saying, I can route my power wherever I want. A little bit like you can route traffic, or you can route other goods, or you can route internet traffic, these kind of things. So it becomes a different kind of problem. Yeah. So it's a simplification. It's a relaxation of the DC approximation, I would say. And it's kind of interesting here that it doesn't make a difference. Like, I think it's my take on that is that it's probably because the grids end up looking kind of radial, and because they look kind of radial, then it doesn't really matter if you have the voltage angles or not. Yeah. Okay. Great. Well, thanks for the question. Okay. So then I'll try and just talk a little bit more about some other things that we are doing here, in case you are interested. So as we talked about, distribution lines are really the ones that are most likely to cause ignitions. So the models that I've just discussed, they extend to distribution grids, but you have to include a lot of other questions then. You have to think about sectionalizing, which means you can only, there's not all lines that have switches, so you can only de-energize kind of parts of the grid together. And that means also shedding all of the load there then together. So here's one reference on this. We have another paper also that has looked at this and kind of trying to understand these trade-offs. So that's kind of an interesting question, and I think an important question to be serious about this. You kind of really need to consider distribution, and maybe also in combination with transmission. As we have discussed, how you define risk metrics really impacts the results, and what the best way is, I am not entirely sure. But yeah, this is a paper from the previous PSSC that also discusses, that gives some insights into that. You might have wondered, when I was modeling risk based on this big wildfire risk map. And that is a rather crude way of modeling risk. Wouldn't it be much better if we model individual ignitions, and I say the probability of an ignition at this point is X, and then I model how a fire would spread, and then I can make my de-energization decisions based not only on the probabilities of ignition and on the resulting fire more directly. And so we have some collaborations, or we have been working with some collaborators on doing this. And again, another paper that will be presented at PSSC next week, as well as a journal paper to reference here, where we were looking at essentially thinking this, where we were modeling different, this as kind of a two-stage or multi-stage program, where we are using what is called stochastic disruptions, where there's a stochastic probability that at any point in time there will be a wildfire risk ignition, and then we model the operation of the grid after that as well. I think this is a better way of modeling risk. It is also computationally very intense. And so I think here we are kind of down to a question like, what is better, and where is the trade-off between having a more detailed risk model and versus a solvable problem. And so I think we often get there in power systems optimization, and here's another example of that. But yeah, happy also to talk more about that if anyone is interested. And then a little bit more also to Rodrigo's question about can you just de-energize some lines without actually having to shed load? That is something you could in many cases do because we have redundancy. I mean, we know that we can turn off many lines in the power transmission grid, and then it won't have any impact on load serving load, because we have built a meshed grid to be redundant, to be n-1 secure. And so as we have been doing this work, we've very often encountered the question, what about n-1 security? Did you consider that? So we ended up doing a study on that, and it's kind of interesting. The bottom line is that if you want to be n-1 secure, you have to shed more load ahead of time to achieve a certain level of wildfire risk. And so I think it's probably you would wait for that fault. I don't know. Interesting questions to ask. But or probably not. I don't know. So there's a lot. Here you get into a lot. Probably you need to go beyond power flow modeling to really understand what should happen here. I also just wanted to mention, I mentioned a few times that we have a bigger test case that we've been working on. We have a test system which we call the CATS, the California Test System. It is published in Transactions on Energy Market Policy and Regulation. And essentially what we did here was, because we wanted to do these wildfire risk studies and we wanted to do them sort of credibly, and be able to look at things like how many people maybe lost power. And then it also comes down to, when you're looking at these wildfire risk assessments, it really matters where exactly does a power line go through, not only which points does it connect. And our hypothesis is that it's not only for wildfire risk mitigation that this matters, it also matters for a whole host of other problems, to have this geographically accurate test system. And so what we did is that we pulled a lot of data, publicly available data on transmission topology in California. When you look at this picture, it looks like, hey, I can just take it and run a power flow. It looks really appealing, but no. It took a couple of years of work. You could talk to Aditya more about it, the nitty-gritty details of it. Lots of thinking about how do we actually put this together in a way that we can run power flow on it. And the good news is that if any one of you are interested in running an optimal power flow for a year worth of data on the California grid, or something like it, here you go. So all of this data is available. You can find the data on GitHub, and you can also find wildfire risk data associated with the system. We are really interested in making this available because we hope that our work can benefit not only us, but all of you as well. So if you have any questions about it, please come and talk to me, or also Aditya here. very happy to share more details about this. Essentially, one of the good things here is that we have tried to make it as realistic as possible, but there's nothing real in there, so you can publish as freely as you want on this task. Okay, so I had kind of said I'm going to do another part, case studies, but I think I always knew it was going to be a lot of material here, and I wanted to, for us to be able to have a little bit of discussion. So this is not really we're not gonna go into any detail here, but I maybe want to just say one thing here, because this is again related to topology optimization, and I think about trying to exploit the structure of a problem in order to get close to optimal solution quickly. And so essentially, the problem that we have been looking at here is about how you do optimal restoration ordering. So essentially, imagine a system where a lot of your system is out because of a storm, because of a public safety power shutoff, because of something, and you actually have to go out and fix things. Which line should you go and fix first? And so if any of you have had a power outage, you know that this can take a lot of time. We had tornado warnings in Madison last week, which left lots of people without power for a lot of time because of it. Thankfully, we didn't get the tornado, but we had a lot of very high winds and a lot of trees that fell down. And then it takes a really, really long time for people to come about, the utility to come. And in some cases, it's kind of obvious where you should go first. You kind of want to prioritize repairs that serve many customers. But in some cases, if you're looking at more widespread outages, for example, a public safety power shutoff, I think is a really good example of this, then you have to prioritize where people go first. So power system restoration takes time. And essentially the idea here is that you want to find a sequence of repairs that maximizes the amount of power that you are able to serve to customers over time. I'm going to just say this is a really, really, really hard problem because you have a mixed integer optimization problem where you are looking at each time step, you have this mixed integer optimization problem where your mixed integer decisions are which line am I going to go and repair? And then because you are looking at the sequence of repairs, all of these time steps are actually coupled. So you have to have like a number of time steps that reflect the number of components that are out. So if you're looking at something where you have a lot of things that are out and damaged, you have to think about a lot of different time steps. And so this makes the problem very, very challenging to solve. And so essentially, there are two things we have explored in terms of how you can go about solving this. So the option one is, again, to kind of look at different power flow approximations, relaxations. And since we have talked a bit about that before, we are not going to go into that. The one thing I do want to talk to you a little bit about is to use a heuristic in order to try to reduce the number of time steps that we have to consider simultaneously. So if I want to solve this full problem, I have to take all of the time steps, couple them together, and put them into one big optimization problem. But now I want to kind of look at, can I make it simpler? And so one option here is, of course, to do greedy optimization. In the first time step, let me just solve my problem and repair one component. And then next time and one more, and one more. The problem there is that sometimes you want to maybe, if you look at repairing 3 lines together, they are going to really have an impact on the amount of load that you can serve. But if you repair any of them individually, they wouldn't. And so that is a reason why this kind of optimizing the whole sequence is important. And so I am not going to go through the power flow formulation here, but I do want to talk about our ideas here on trying to reduce the number of restoration periods that you have to consider simultaneously while avoiding falling all the way into this kind of greedy thing, where you kind of try to keep some information about the sequence. And so essentially, the algorithm that we came up for this is we called it recursive restoration refinement. And so essentially the idea here is that you start out, you have n components in the power grid that you need to repair. And in the first step, you're only going to split your repairs into 2 groups. And you're going to say, this half of components needs to be repaired first, and this half of components can wait until later. And essentially what you're doing is that you're maximizing the amount of load that you're able to serve halfway through your restoration process. And then you can take those again, and you can, again, split it into a first half and a second half. And so now we have we're kind of maximizing load served at 4 different points, like after 1/4 has been repaired, after half has been repaired, after 3/4 have been repaired, and after all has been repaired. And then you keep going like that until you have split everything. You have gone this tree all the way down to 1 component each. So you're solving a lot of different optimization problem here, but every time you're only considering 2 periods. And so as we're doing this, I mean, we're really hoping that solving many smaller problems is easier than solving one big one, and that we are able to maintain some kind of benefit here because we're looking at restoring groups of components together. Did I see a question up there? Or no? Was it? No. Okay, good. I know I will not hold you back from lunch. This is the bottom line, okay? So does it work? So we were comparing this method against some other methods, and I see the colors here have not really worked well. So ROP here is solving the full problem. And we were comparing this recursive restoration refinement with this solving the full problem, as well as with kind of a state-of-the-art heuristic algorithm and the simple kind of industry heuristic where you're just kind of repairing the largest component first. And essentially, the bottom line is that our solution algorithm that splits this up into half achieves a very high solution quality solutions in very short time. So we're essentially saying that by splitting this sequence always in half, we are able to solve it 1,000 times faster than the best known heuristic. And it really tends to find good solutions within 5 minutes of solve time. So here, this is essentially the % of power served, so the quality of our solution that we find, and the time limit. And you can see that our recursive restoration refinement finds the best solution we know of in 15 seconds, whereas trying to solve the full problem, we are still trying to get there after 28,000 or 29,000 seconds. And so essentially, what we found is that when you're looking at a whole range of different systems, different levels of damage, our solution always are within 1% of optimal, of the best known solution. In some cases, we don't know if it is optimal. It's just we are within 1% of the best solution we were able to find. And this is, if we take a 10-hour time limit, you can see everything that is grayed out here are kind of good solutions. And you can see that essentially what it means that there are many gray spots means that there are many of these algorithms that performed well. But if I now go and I say I only actually have 5 minutes to solve this problem, it turns out that our algorithm is kind of the only workable one. So yeah, so I wanted to just say this because I think it's an example of how you can leverage structure of a problem in order to try to think about what is it actually that is important that we find here, and then you can try and build algorithms around that. So it's a little bit of a custom thing here. Sorry, now I have really hammered on you a lot, and I'm gonna, we are past 12, and I know that there is lunch coming. So what I wanted to say is just that I hope you got the impression that problems involving topology optimization can be important, fun, and challenging. So I think this is really it's really, really hard. And that's kind of good for us because we are researchers, right? I mean, if it's not hard, where's the fun? Right. So being able, and I also firmly believe that being able to solve those problems more efficiently can improve a variety of aspects in power systems operation and planning. And there's just really a huge room for improvement. So we know that solvers are getting better, but we still really struggle with solving even moderately sized problem. And then I'm going to say that I believe in optimization and formal optimization. I also like machine learning. There's a lot of cool things about it, but there's something about being able to talk about optimality gaps and kind of measuring that. So I think that if you are a person working on machine learning, this could be a cool problem to look at, but just also maintain always in the back of your mind that optimality is kind of cool as well. And in particular, actually integer optimization internally relies on a lot of heuristics. And so there's a lot of work going on the integer optimization side of thing in terms of trying to leverage machine learning to improve those heuristics. So that's for anyone who's kind of interested in that side of things. I wanted to put in a little bit of machine learning in here as well. All right, and then I'm going to say, test it out. Most of the code for everything you've seen is online on GitHub. All the plots were made with power plots. So if you are a person who's doing power system optimization and you really want to look at your solution, I really recommend that package. So yeah, take a look at it. And with that, I'm going to say thank you and have a good lunch.